Let's now prove that weak string erasure is secure against cheating Bob. So what do we want to show? We want to show that Bob has difficulty guessing the string X that Alice has in her possession. And I will assume now that Bob only has Q qubits of quantum storage. Again, if we want to analyze the security of quantum protocols, it helps to think like an adversary. So let's, for the moment, think what would happen if Bob had a perfect quantum memory. He can store n qubits. So let's imagine that we are cheating Bob and we are trying to attack the protocol. Meaning, we have to come up with a strategy for Bob to guess the entire string X. I've again removed the steps of the cheating party from the protocol, since we can fill this in ourselves now in an effort to guess X. You may want to think about it for a second on what we should do before continuing. If we are cheating Bob and we do have an arbitrary quantum memory, note that one thing we can do is simply store all the qubits that Alice sends us without measuring anything. So what we're going to do is we're going to store all the qubits all through the waiting time until Alice announces her basis string theta. And then we're going to measure every qubit in the right basis to learn the entire string X. So if Bob has a perfect quantum memory, it is certainly not possible for his min entropy to be larger than 0. So something magic has to happen in this waiting time. With the storage assumption, we take advantage of precisely this step. Our security analysis is very similar to the one of 1 out of 2 oblivious transfer. In fact, it's even simpler. So let me just remind you. We first purify the protocol, so we imagine again that instead of preparing BP84 states, Alice prepares EPR pairs. We then give Bob a bit of extra power to in fact prepare the states that Alice is going to measure herself. And this way we ended up at the uncertainty game. So in the end, we again have security from quantum uncertainty. So this min entropy, without the Q, can be evaluated from the uncertainty game. And of course, how much uncertainty we obtain depends on how incompatible these measurements are. And for BP84 measurements, we saw that this here, n is the length of the string, is roughly 0.22 times n. To get rid of Q, we again just subtract the storage size. So this is the number of qubits that Bob can store. So we can see that the protocol is secure as long as his storage is just small enough. So we secure, I mean here that the min entropy minus the number of qubits Q that he can store is still positive. Weak string erasure is useful for example, obtaining bit commitment and string commitments as long as the min entropy is positive. So we saw an attack if Bob can store n qubits. The analysis that we see here gives us a little bit less because we want that his storage is less than 0.22 times n in order to be secure. It turns out that there is an analysis, which you can find in a pointer to the lecture notes, that makes the min entropy positive as long as Q is actually smaller than n minus roughly log n many bits. And this is essentially optimal, since we saw an attack if Bob can store all n qubits. Weak string erasure is very powerful, making this the only part of the quantum security analysis. All other protocols can be built on top of weak string erasure using simpler methods. For example, we can obtain a string commitment using standard methods using just classical communication. Our usual tricks of error correction, privacy amplification allow us to just from the simple primitive go to any protocol.